In this tutorial, I will give a simplified explanation of what the parameters mean in the global and local JSON configuration files. The Semtech UDP Packet Forwarder, the code can be found at this GitHub page, is configured by this global configuration file. It has two sections, the radio settings, indicated by this parameter, and the server settings, indicated by this parameter. The radio settings should contain the parameters for the LoRa concentrator board, for example, RF channel definitions, modem parameters, etc. The server settings should contain the gateway parameters, for example, IP address of the server, keep alive time, etc. If parameters are defined in both the global and local configuration file, the local definition overrides the global definition. Recommended is to make changes in the local configuration file. Here is an example of a global and local configuration file. Here is a link to a global configuration file, and here is a link to a local configuration file. Here is an example of a global configuration file. Here are the radio settings, and here are the server settings. And here is an example of a local configuration file. Let's start with this parameter. It contains the gateway ID or gateway AUI and is based on the MAC address. The gateway identifier is sent in each message to the network server. The default value is 0, and more information can be found in tutorial 28. This parameter contains the network server hostname or IP address. The default IP address is 127.0.0.1, and more information can be found in tutorial 28. This parameter contains the network server port for uplinks. The default port is 1780, and more information can be found in tutorial 29. This parameter contains the network server port for downlinks. The default port number is 1782. More information can be found in tutorial 29. This parameter contains the keep alive interval in seconds for downlinks. It sends a keep alive message, meaning a pull data packet, every X seconds from gateway to the network server to ensure downlinks. The default value is 5, and more information can be found in tutorial 29. This parameter contains the timeout value in milliseconds for uplinks, meaning push data. The default value is 100. The push timeout millisecond parameter specifies the timeout limit in milliseconds on how long the LoRaWAN network server waits for the push data operation to complete, as you can see over here. More information about push data, see tutorial 29. This parameter contains the auto-quit threshold. If the number of non-acknowledged pull data packets exceeds the threshold, it auto-quits. The default value is 0. Here's an example. Let's assume auto-quit threshold is 5. An auto-quit counter counts the number of pull data packages sent since the latest pull acknowledge, as you can see over here. If the auto-quit counter is bigger than the auto-quit threshold, the concentrator will be stopped. More information about pull data and pull acknowledge, see tutorial 29. This parameter contains the interval in seconds for status information or statistics display. The default value is 30. So every X seconds, the gateway statistics information is logged in the syslog file. The start of the statistics information is indicated by this line, and the end of the statistics information is indicated by this line. A stat.json object with gateway status information is sent to the network server, and more information can be found in tutorial 29. The last seen message in the TTN console is updated, and more information can also be found in tutorial 29. This parameter contains a boolean. If true, packets received with a valid CRC will be forwarded. CRC stands for Cyclic Redundancy Check and is an error detecting code to detect accidental changes to raw data. The default value is true. This parameter also contains a boolean. If true, packets received with CRC error will be forwarded. The default value is false. This parameter also contains a Boolean value. If true, packets received with no CRC will be forwarded. The default value is false. So here's an example. The gateway sends a packet to a LoRaWAN network server. The packet consists of a payload and a payload CRC. I will give you 3 examples. This is the first example. Should the packet be forwarded if payload CRC is okay and this flag is true? If the payload CRC is okay and this flag is true, then this packet will be forwarded. Here is example 2. Should the packet be forwarded if payload CRC is not okay and this flag is true? The answer is yes. If this CRC is not okay and this flag is true, then this packet will be forwarded. Here is example 3. Should the packet be forwarded if payload has no CRC and this flag is false? So if this payload has no CRC and this flag is false, then this packet will not be forwarded to the LoRaWAN network server. For more information about payload CRC, see tutorial 17. This parameter contains the GPS module TTY path. If the path is set, the GPS module is enabled. If this parameter is not found, GPS is disabled for this gateway and the TTY port is not open for GPS synchronization. For example, for the REC 831 concentrator, the GPS TTY path, you can use this path. This parameter contains the gateway reference latitude in degrees. This parameter contains the gateway reference longitude in degrees. And this parameter contains the gateway reference altitude in meters. This parameter contains a Boolean. If true, the gateway will use the hard-coded reference latitude, reference longitude, and reference altitude instead of the real GPS coordinates. The 5 keys mentioned above are explained in tutorial 28. This parameter contains the beacon signal period in seconds. The default value is 0. The allowed values must be bigger or equal than 6. This parameter contains the beaconing signal, which will be emitted at specified transmit frequency in Hz, and this is its default value. This parameter contains the number of beacon channels. The default value is 1. This parameter contains the frequency step between beacon channels in Hz. The default value is 0. And this parameter contains the beacon data rate, meaning the spreading factor. The default value is 9. The keys mentioned above will be explained in a future video when demonstrating Class B devices. This parameter contains the beacon modulation bandwidth in Hz, and the default value is 125,000. This parameter contains the beaconing transmit power in dBm. The default value is 14. And this parameter contains the beacon information descriptor. The default value is 0. The keys mentioned above will be explained in a future video when demonstrating Class B devices. This parameter contains a Boolean. Enable only for public networks using the LoRa MAC protocol. If false, the sync word is this hex value. If true, the sync word is this hex value. The default value is false. If you connect to a public network, such as the Things network, then this parameter is set to true. If you connect to a private network, then this parameter must be set to false. This parameter contains the index of the radio. The value can be 0 or 1, which provides the clock to the concentrator. The default value is 0. Please note radio 1 provides the clock to the concentrator for most devices except multitech. For multitech, set to 0. Here is an example. The SX1301 is a baseband processor and not a radio. It has no RF interface. In this example, the SX1301 has 2 radios, radio 0 and radio 1. If the clock source is 1, it means radio 1 provides a clock to the SX1301 for the analog to digital converter. So radio 1 provides a clock to the SX1301. This parameter contains the antenna gain in dBi. More information about dBi, see tutorial 5. Antenna gain value is subtracted from the transmit power value, which the network server requests from the gateway. It affects the downlink, not the uplink. The default value is 0. A more detailed explanation of the antenna gain will be given when explaining the lookup table keys. Listen before talk, or LBT, is a mandatory requirement in some countries, such as South Korea. See LoRaWAN 1.0.2 Regional Parameters document. LBT prevents end devices from transmitting at the same time on the same channel. LBT means the end device checks, meaning listen, if the intended channel is free. If the channel is not free, the end device changes to another channel and repeats the LBT procedure. If the channel is free, it transmits, meaning talk. Now let me explain these LBT configuration parameters. Make sure the concentrator supports the LBT feature and LBT is supported in your region. For example, the REC 831 concentrator does not support LBT, as you can see over here. In case you wonder how I got previous log message, I have done the following. For demonstration purpose, I have copied the LBT_CFG values from this JSON file into my global configuration JSON file and set the enable parameter to true. I've copied these parameters and enable is set to true. Next, I have set this flag to 1 in the library.cfg file and compiled the code. See tutorial 28.2. This parameter contains a boolean. If true, LBT is enabled. The default value is false. This parameter contains the RSSI threshold in dBm to detect if the channel is busy or not. Below this threshold, transmit will be allowed. If the enabled parameter is true, this parameter is set. The default value is 0. More information about RSSI can be found in tutorial 10. Please note the RSSI target parameter is an LBT configuration parameter. Here is end device A. The end device is configured with these 8 channels, each with a different frequency. First, the end device selects a frequency to transmit, for example, this frequency. The device scans this frequency. At the same time, there are 2 devices, device B, which transmits at this frequency, and there's another device, device D, which transmits at another frequency. As you can see, this frequency is the same as this scan frequency. Device A receives the signal from device B. It reads the RSSI value. So the scanned RSSI value is minus 50 dBm. Device A compares the scanned RSSI value with the RSSI target, which is minus 80 dBm. The scanned RSSI value must be smaller than the RSSI target value, which is not the case. Device A will not use this frequency. Device A selects another frequency to transmit. It checks the list and selects this frequency. At the same time, there is another end device which transmits at this frequency. This frequency matches this frequency. Now device A scans this frequency. Device A receives a signal from device C. So the scanned RSSI value is in this case minus 100 dBm. Again, it compares it with the RSSI target value, which is minus 80 dBm. In this case, the scanned RSSI, which is minus 100, is smaller than the RSSI target, which is minus 80 dBm. So device A can use this frequency. Device A can now transmit at this frequency. This parameter contains the RSSI offset in dBm to apply to RSSI reading from the radio front end. If the enable parameter is true, then this parameter is set. The default value is 0. This parameter contains the center frequency to track for LBT. The default value is 0. This parameter contains the channel scan time in microseconds to track RSSI before transmit. The allowed values are 128 or 5000. The default value is 0. So these are the center frequencies to track for LBT, and these are the channel scan times in microseconds. These are the radio parameters. This parameter is a Boolean. If true, radio is enabled for use. The default value is false. This parameter contains the center frequency of the radio in Hertz to listen for packets. The exact frequency the gateway transmits on is specified by the network server. If the enable parameter is true, this parameter is set. This parameter contains the board-dependent RSSI offset in dBm to adjust the radio RSSI reading. If the enable parameter is true, this parameter is set. The end node transmits a message. The gateway receives the message. It also measures the RSSI. The measured RSSI will be adjusted by RSSI offset and additional offset. The gateway creates a push data packet containing the adjusted RSSI, which is sent to the LoRaWAN network server. For more information about RSSI, see tutorial 10. For more information about push data, see tutorial 29. Here's an example of a push data packet. The RSSI parameter is the adjusted RSSI. It is the measured RSSI plus the RSSI offset minus additional offset. And the additional offset is a hard-coded value, which is -35. This parameter contains the radio type. You can choose between this type and this type. If enable parameter is true, then this parameter is set. The SX1257 and 1255 radios captures the LoRa uplink packets and sends the digital signal to the SX1301 digital baseband chip, which demodulates the signal. This processed signal is used by the microcontroller unit. The SX1257 chip can be configured to any frequency inside the 868 or 900 MHz ISM band. The SX1255 chip can be configured around the 433 MHz ISM band. Most commercial concentrators using the SX1301 chip is built according to one of the three above-mentioned configurations. 2 radios both using the SX1257, or 2 radios using the SX1255, or 1 radio using the SX1257 and the other radio using the SX1255. In this configuration, it is called dual band. For example, if you buy the REC A31 Pilot Gateway operating in this frequency range, the concentrator uses 2 SX1257 radios. This is the REC A31 Pilot Gateway, which is configured for the AU868 frequency range. The gateway has a REC A31 concentrator, which has a SX1301 digital baseband chip and these 2 radios. A radio signal is received by these 2 radios and processed by this chip. The data is then sent to the packet forwarder, and the packet forwarder sends this data to the LoRaWAN server. This parameter is a Boolean. If the enable parameter is true and the transmit enable parameter is true, the radio can be used for transmissions. The default value is false. These are the parameters for radio 0, and these are the parameters for radio 1. This is radio 0 and this is radio 1. The enable parameter is set to true and the transmit enable parameter is set to true, which means this radio is used to transmit data. In radio 1, the enable parameter is set to true, but the transmit enable parameter is set to false, which means this radio does not transmit data. This parameter contains the transmit notch filter frequency in Hertz. If the enable parameter is true and the transmit enabled parameter is true, then this parameter is set. This parameter is used by FPGA. The allowed values are within this range. Notch filtering is performed by an FPGA. As you can see, the REC 831 concentrator has no FPGA. To check if a concentrator supports FPGA, set this flag to 1 in the library.cfg file. See tutorial 28.2. Unfortunately, I cannot provide you more information about notch filtering. This parameter contains the minimum frequency allowed for transmissions. If the enable parameter is true and the transmit enable parameter is true, then this parameter is set. This parameter acts as a failsafe if the network server tells to use a frequency that falls outside the minimum transmission frequency and the maximum transmission frequency range. This parameter contains the maximum frequency allowed for transmissions. If the enable parameter is true and the transmit enable parameter is true, then this parameter is set. This parameter also acts as a failsafe if the network server tells to use a frequency that falls outside the minimum transmission frequency and the maximum transmission frequency range. In radio 0, enable parameter is true and the transmission enable parameter is true. The minimum transmission frequency is set to 863 MHz and the maximum transmission frequency is set to 870 MHz. If the network server requests the gateway to transmit at 868.1 MHz, it is within this range. The gateway will execute this request. But if the network server requests the gateway to transmit at 860 MHz, which falls outside this range, then the gateway will not execute this request. Only if enable is set to true and the transmit enable is set to true, then this radio is used to transmit data. If transmit enable parameter is set to true, then these three parameters are used. If enable parameter is true and the transmit enable parameter is set to false, then this radio is not used to transmit data. In the global configuration JSON file, you can find the intermediate frequency channels. These intermediate frequency channels. All gateways must comply to certain rules and regulations when using the ISM band frequencies. These rules and regulations determine how the intermediate frequency channels came about. As already explained in tutorial 3, in Europe, the European Telecommunication Standard Institute, ETSI, creates these standards which are used by the local regulatory authorities. In the US, the Federal Communications Commission, FCC, creates these standards. Most countries are using the standard set by either ETSI or FCC. In the following demonstration, I assume the gateway is operated in the Netherlands, a European country. In Europe, the ISM band frequency range is between 863 and 870 MHz. Therefore, the intermediate frequency channels mentioned in this global configuration JSON file must comply with the rules and regulations set by the Dutch authority, ETSI, and others. In the next slides, I will demonstrate this. Let's start with ETSI. For LoRa-related ETSI documentation, search for standard number 300220 at this web address. By the way, the number 2 means the second part of this multi-part document. This is the etsy.org website. Let's search for the document. Enter the document number 300220 and select this option and press the search button. This is part 1. Again, part 1, but a newer version. Part 1, another newer version. This is part 2. Part 2, newer version. Okay, this is the document we need. The document is called Short-Range Devices Operating in the Frequency Range 25 MHz to 1000 MHz, Part 2, Harmonized Standard for Access to Radio Spectrum for Non-Specific Radio Equipment. When you download this document and search for Annex B, Table B1, you can find the allowed power and duty cycles for the 863 to 870 MHz frequency range. I have put the relevant information in this table. Now let's look at the Dutch laws and regulations. For Dutch laws and regulations regarding LoRa, go to this web page. In Attachment 11, Subcategory 1, you can find the allowed power and duty cycles for the 863 to 870 MHz frequency range. Again, I have put the relevant information in a table. In this table, you can find the Dutch law and regulations with regard to this frequency range. And in this table, you can find the ETSI 300220 standard with regard to these frequency ranges. The frequency range, ERP, and duty cycles are the same, which means if I comply with the ETSI standard, I also comply with the Dutch law and regulations with regard to these frequencies. The LoRa Alliance created a set of standards ensuring interoperability of all LoRaWAN products and technologies. For example, they created the LoRaWAN Regional Parameters document. See this webpage. This is the LoRa Alliance website. Select this option, LoRaWAN for developers. Here you can download the latest LoRaWAN specification document. And here you can download the latest LoRaWAN Regional Parameters document. You can also find this document in the Resource Hub and filtered on technical documentation. See this webpage. Here is a link to the Resource Hub page. Filter on technical document, and you can find all technical documents. In the LoRaWAN 1.0.2 Regional Parameters document, revision B, for the AU 863 to 870 ISM band, the following is specified. The AU 863 to 870 ISM band channel frequencies applies to any region where the ISM radio spectrum use is defined by the ETSI 300220 standard. For the AU 863 to 870 ISM frequency band, a maximum of 16 channels is supported. 3 default channels must be implemented in every AU 868 MHz end device. Those channels are the minimum set that all network gateways should always be listening on. So every LoRa device must always implement these 3 channels, with this bandwidth and these data rates. And the duty cycle must be less than 1%. And the remaining 13 channels can be freely attributed by the network operator, for example, the Things network. So for the AU 863 to 870 ISM frequency band, the following encoding is used for the data rate. So data rate 0 means spreading factor 12 and a bandwidth of 125 kHz. Data rate 1 means spreading factor 11 and a bandwidth of 125 kHz, etc. As you can see, the bandwidth are the same, 125 kHz, except this one. The bandwidth is 250 kHz. The modulation type is all LoRa over here, and the modulation type is here FSK. The receive 1 window uses the same channel as the preceding uplink, and the data rate is a function of the uplink data rate and an offset. To keep this tutorial short, I will not elaborate on this. The receive 2 window uses a fixed frequency and data rate. The default parameters are 869.525 MHz and the data rate is 0, meaning spreading factor 12 and a 125 kHz bandwidth. Now let's look at the Things network. A list of frequency plan definitions used by the Things network can be found at this address. These are the AU 863 to 870 frequency plan definitions. And here are the US 902 to 928 frequency plan definitions. And you can see there are more frequency plan definitions. These frequency plans are based on what is specified in the LoRaWAN regional parameters document. It is important to understand that a frequency plan is intended for the LoRaWAN network server, but also applies to the gateway, end-to-end node. Otherwise, these three entities cannot communicate with each other. The Things Network AU 863 to 870 frequency plan can be found in this table. These are the uplink channels and corresponding data rates. For the downlink, you can use the same uplink channels 1 to 9. It is used for receive window 1. For receive window 2, this frequency and this data rate is used. Now let's go through these nodes. Let's start with node 1. The Things Network uses the non-standard spreading factor 9 bandwidth 125 data rate for receive window 2 in Europe instead of spreading factor 12 bandwidth 125. As mentioned earlier, if your devices uses over-the-air activation, this will be configured automatically when they join. If your devices use activation by personalization, you will need to program this receive window 2 data rate into the devices in order to make them work with the Things Network. This will be explained in another tutorial. Node 2. The receive window 1 data rates, these data rates, complies with LoRaWAN AU 863 to 870 regional parameters document. Node 3. The bold values, these values, are mandatory according to the LoRaWAN AU 863 to 870 regional parameters document. Node 4. More information about receive window 1 and receive window 2, see tutorial 4. Node 5. There is one channel with a fixed spreading factor and bandwidth. This channel is called standard LoRa channel. This channel has a fixed spreading factor and bandwidth. For example, this channel uses spreading factor 7 to spreading factor 12, but the bandwidth is the same. The same applies to this channel. The spreading factor is 7 to 12, but the bandwidth is the same. In this table, you can find the Things Network AU 863 to 870 frequency plan for uplink. And in this table, you can find the ETSI 300220 standard. If you look at these frequencies, it lies within this frequency range. And this frequency lies within this frequency range. So for uplink frequencies, the Things Network AU 863 to 870 frequency plan complies with the ETSI 300220 standard. Within this frequency range and this frequency range, the ERP is 25 milliwatts, as you can see over here. According to previous table for uplink, for frequency range 865 to 868.6 MHz and 868.7 to 869.20 MHz, the maximum allowed ERP is 25 milliwatts. More information about ERP, see tutorial 9. So 25 milliwatt ERP is approximately 14 dBm. For more information, see tutorial 5. Now let's do the same again, but now for the downlink. So channel 1 to 9 is used for receive window 1, and this frequency is used for receive window 2, and it uses this data rate, as explained earlier. These frequencies lies within this frequency range, this frequency lies within this frequency range, and this frequency lies within this frequency range, which means for downlink, the Things Network AU 863 to 870 frequency plan complies with the ETSI 300220 standard. In this table, you can find the Things Network uplink and downlink frequencies, which complies with the LoRaWAN regional parameters document. As you can see, the Things Network defined 8 uplink LoRa channels. This frequency is used for receive slot 2 for downlink purpose. This table and this table contains the LoRaWAN regional parameters for AU 863 to 870. These are the three mandatory frequencies. As you can see, these are the three frequencies. And these frequencies must use data rate 0 to data rate 5. These data rates. So spreading factor 7 to spreading factor 12 with a 125 kHz bandwidth. And as you can see, it complies with these rules. These frequencies are set by the network operator, in this case the Things network. Commercial LoRa gateways uses the SX1301 or SX1308 chip. This video is made in March 2019. The SX1301 is intended for outdoor usage. The ambient operating temperature is -40 to 80 degrees Celsius and it has a -142 dBm sensitivity. The SX1308 is intended for indoor usage. The ambient operating temperature is 0 to 70 degrees Celsius and has a -139 dBm sensitivity. According to the Semtech datasheets, both the SX1301 and SX1308 can scan up to 8 LoRa channels for preambles of all data rates at all times. Because of this, the Things network defined 8 uplinked LoRa channels for the AU 863 to 870 frequency plan. So what have we learned? Well, for the ISM band 863 to 870 MHz frequency, the European Telecommunications Standards Institute issued standards, in this case the ETSI 300220 standard. The Dutch authority also issued Dutch laws and regulations with regard to this ISM band. The same applies to the LoRa Alliance. Their standards can be found in the LoRaWAN Regional Parameters document. The network operator, for example the Things network, also issued their own frequencies, which complies with previous mentioned rules and regulations. And then you have the Semtech datasheets. The chips used have specific hardware capabilities. If you take all these information into account, you will get the global configuration.json file. And in this file you find the radio parameters, the channel multi-spreading factor parameter, the channel LoRa standard parameter, and the channel FSK parameter. The value set in these parameters depends on this information. My apologies to you all. I'm also getting bored about frequencies, laws, and regulations. You have no idea how much time I spent going through these documents. Now let's get down to business. These are radio 0 parameters, and these are radio 1 parameters. You can find these parameters in the global configuration.json file. Radio 0 is this row, and radio 1 is this row. This is radio 0 center frequency, which you can find over here, but the frequency is in megahertz. And this frequency is this frequency in megahertz. The transmit enable parameter is true, that is yes over here. And the transmit enable parameter is false, which is no over here. Please note, both radios will be used for receiving packages, but only one radio, in this case radio 0, will be used for transmitting packages. I am only showing you 3 channel multi-spreading factor parameters. Index 0 is this index 0, index 1 is this index 1, and index 3 is index 3. For index 0 it uses radio 1 and the intermediate frequency is -400,000 Hz. So index 0 minus 400,000 Hz is -0.4 MHz. Index 1 uses radio 1 and the intermediate frequency is -200,000 Hz. So index 1 is this index, the intermediate frequency is -0.2 MHz. Index 3 uses radio 0 and the intermediate frequency is -400,000 Hz. So it uses radio 0, index 3, the intermediate frequency is -0.4 MHz. 868.5 minus 0.4 is 868.1 MHz. 868.5 minus 0.2 is 868.3 MHz, and 867.5 minus 0.4 is 867.1 MHz. This is how these frequencies are calculated. By the way, index 0 to 7, the bandwidth is always 125 kHz, and the spreading factor is always 7 to 12. Both values are hard-coded in the Semtech Packet Forwarder software. Please note, for the channel multi-spreading factor parameter, the intermediate frequencies allowed values are minus 400,000 to plus 400,000 Hz. The user cannot set this bandwidth and spreading factor. As mentioned earlier, these values are hard-coded. There's only one channel LoRa standard and only one channel FSK. Channel LoRa standard is this column. It uses radio 1 and the intermediate frequency is minus 200,000, which means minus 0.2 MHz. So 868.5 minus 0.2 is 868.3 MHz. The bandwidth is 250 kHz and the spreading factor is 7. We do the same for channel FSK, that is this column. It uses radio 1 and the intermediate frequency is 300,000, that is 0.3 MHz. So 868.5 plus 0.3 is 868.8 MHz. The bandwidth is 125 kHz and the data rate is 50 kilobits per second. The frequencies mentioned in this table are uplink frequencies. It means the gateway scans these frequencies to check if there are end nodes sending packets at these frequencies. A gateway can also create downlinks whereby packets are transmitted from the gateway to end nodes. But these downlink frequencies are set by the LoRaWAN network server in the pull response messages. See tutorial 29. That is this pull response message from the LoRaWAN network server to the gateway. The gateway only checks if the downlink frequency is within a certain frequency range specified in the global configuration JSON file, as you can see over here. In this setup, the end node sends data to the Things network. The end node uses Arduino LMIC. The Arduino LMIC can be found at this GitHub page. And the gateway uses the Semtech software. LoRa gateway can be found at this GitHub page, and the packet forwarder can be found at this GitHub page. These 4 frequencies are hard-coded in the Arduino LMIC library. The end node uses these 4 frequencies. These 3 frequencies are used to transmit or for receive slot 1, and this frequency is used only for receive slot 2. When registering the end node using over-the-air activation during join accept, these frequencies are set by the LoRaWAN network server. These frequencies are not hard-coded in the Arduino LMIC. These frequencies are set by the LoRaWAN network server. These 5 frequencies are used to transmit or for receive slot 1. In the gateway, these frequencies are set in the global configuration.json file. The gateway scans these frequencies, but the gateway can also transmit at frequencies which are set by the LoRaWAN network server through the pull response message. For example, if the LoRaWAN network server sends a pull response message specifying to transmit at 868.1 MHz, then the gateway will receive this pull response message and transmits at 868.1 MHz. The uplink frequencies, bandwidths, and spreading factors specified in the global configuration.json file complies with the Things Network AU 863 to 870 frequency plan, as you can see over here. So these frequencies matches with these frequencies, and these data rates matches with these data rates. In the most basic form, a LoRaWAN gateway is just a digital radio transceiver, and in general, This is what a digital radio transceiver looks like. It has a transmitter and a receiver path. So when you transmit data, data flows this direction. And when you receive data, it flows this direction. Now let's look at the transmitter path, this flow. Step 1. The digital data that contains the information that needs to be transmitted. Step 2. The digital to analog converter converts the digital data to an analog signal. Step 3. The low-pass filter filters out the noise, etc. from the analog signal. Step 4. A local oscillator generates a carrier signal and modulates the carrier signal onto the analog signal, thus creating an RF signal. Step 5. The power amplifier boosts the RF signal. Step 6. The transmit-receive switch sends the amplified RF signal to the transmitting antenna. The receiver works the same as the transmitter, but in reverse order. By the way, LNA stands for low noise amplifier. But I'm not interested in the receiver path, so I will not elaborate on this. Let's focus on the transmitter. This is the digital gain. This is the digital to analog gain. This is the mixer gain. And this is the power amplifier gain. So the only thing you need to know is if you input a certain value into the DIC gain parameter, if you input a certain value into the DAC gain parameter, if you put a certain value into the mix gain parameter, and you input a certain value into the PA gain parameter, it will output a certain RF power. How these values are determined is not important. The only thing you need to know is if you input certain values inside these parameters, it will output a certain RF power. The parameters DIC gain, DAC gain, mix gain, PA gain, and RF power can be found in the global configuration.json file. Here is such an entry. These are the parameters for lookup table index 9. Please note DAC gain is always 3 and is therefore not found in the configuration file. If a specific RF power is needed, the corresponding power settings, meaning PA gain, mix gain, and DIC gain, can be found in the global configuration.json file in the lookup tables. These are the transmit lookup table parameters. There are in total 16 lookup table entries, starting with index 0. These parameters are board dependent. This parameter controls the external PA gain. The allowed values are 0 to 3 and the default value is 0. This parameter controls the radio DAC gain. The only supported value is 3. This parameter controls the SX1301 digital gain. Allowed values are 0 and 3. The default value is 0. This parameter controls the radio mixer gain. The allowed values are 8 to 14. The default value is 3. By the way, this will cause an error. And this parameter is the measured transmit power at the board connector in dBm. The default value is 0. As mentioned earlier, a maximum of 16 power settings can be configured. These settings are board specific and have been selected during calibration for each concentrator. I have noticed that concentrators based on the Semtech SX1301 reference designs uses the same lookup table power settings. See this link. Semtech created two SX1301 reference designs. The Semtech reference design board SX1301 AP1, PCB_E286, which uses no FPGA, and the Semtech reference design board SX1301 AP2, PCB-E336, which uses an FPGA. The lookup table power settings for Semtech's reference design board SX1301 with no FPGA, see this link. and these are the corresponding power settings. The lookup table power settings for Semtech reference design board SX1301 with FPGA, see this link, and these are the corresponding power settings. Always check the concentrator's manual which lookup table power settings to use. Do not copy the previous lookup table settings. They apply to the Semtech reference design boards. But what is the purpose of these lookup table power settings? When a downlink message is created, a pull response message is sent from the LoRaWAN network server to the gateway, as you can see here. More information can be found in tutorial 29. The transmit packet JSON object has the parameter POW, which is the proposed RF power in dBm. It is the output power the LoRaWAN network server commands the gateway to transmit. Here is an example of this parameter, POW. The value is 14. This means the network server is in charge of requesting transmit powers. The gateway extracts the proposed RF power from the transmit packet JSON object. The proposed RF powers are in fact EIRP values. Let's assume the proposed power is 9 dBm. Antenna gain is 2 dBi, and the gateway concentrator uses the following lookup table power settings. Please note I am using dBi and not dBd because the proposed RF powers are in fact AERP values. In this tutorial, the assumption is made that the network server sends EIRP values and not ERP values. So the antenna gain is subtracted from the proposed RF power to stay within the legal limits. So the antenna gain is subtracted from the proposed power. If the power is 8 dBm and antenna gain is 2 dBi, this includes cable losses, etc., then the RF power is 6 dBm. Now the gateway searches the lookup table for RF power 6 dBm in the global configuration.json file. I will remind you again, these power settings are board specific and have been selected during calibration for each concentrator. As a gateway user, you should not mess around with these settings. So the gateway finds this entry in the lookup table, as you can see over here. The gateway now knows how to adjust the power amplifier gain, the mixer gain, and the digital gain to obtain a 6 dBm transmit output. If the RF power is not found in the lookup table, then an error will be logged, the downlink packet will be rejected, and de facto the package is lost. The following logs are created with Semtech LoRa library version 5.0.1 and Semtech UDP Packet Forwarder version 4.0.1 by changing RF power 14 to -14. As you can see, in the syslog you will see this error message when no corresponding transmit power is found, and this error can be found in the transmit packet acknowledge message. So what does it mean an RF power is 6 dBm? It means the gateway concentrator outputs a transmit power of 6 dBm at this point. So the gateway outputs an RF power of 6 dBm, not including the antenna gain. So the AERP is the RF power plus the antenna gain, and the antenna gain is including the cable losses. The AERP is the RF power plus the antenna gain, and the antenna gain is including the cable losses. It is important to specify the antenna gain in the global configuration.json file, otherwise the AERP does not comply with the regulations. For example, in the AU 863 to 870 region, for frequency range 860 to 868.60 MHz and 868.70 to 869.20 MHz, the maximum allowed ARP is 25 milliwatts, that is approximately 14 dBm. the AERP in dBm equals ARP in dBm plus 2.15. So the maximum allowed AERP is 14 plus 2.15 is approximately 16.15 dBm. Because the antenna gain is specified in dBi, the AERP must be smaller or equal than the maximum allowed AERP. Here's the RF power plus the antenna gain is the AERP, and the AERP must be smaller or equal than the maximum allowed AERP. And the maximum allowed AERP is region specific. When the DIC gain is 0, the DAC gain is 3, the mix gain is 10, and the PA gain is 1, the gateway will output an RF power of 6 dBm. 6 dBm plus an antenna gain of 2 dBi equals 8 dBm. This 8 dBm is the AERP. And you can see the AERP is smaller than the maximum AERP, which is in this case 16.15 dBm. In this example, the AERP is 8 dBm, that is the RF power plus the antenna gain plus the cable losses for the downlink. If the maximum allowed AERP is approximately 16.15 dBm, then this power complies with the AU 863 to 870 regulations. We have here the lookup table. Depending on the requested power, this requested power is searched in the lookup table. From the lookup table, the corresponding PA gain, mix gain, and DIC gain will be found. These power settings are used by one of these radios, radio 0 or radio 1, depending which radio is used for transmission. Let's assume radio 1, then the correct transmit power is used to transmit the packet. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.